So I just wanted to come back to an example that we talked about before when we were looking at subspaces of Fn. So let's take U to be all the points in Fn that satisfy this matrix equation. Okay, so A is going to be some fixed m by n matrix. So suppose we have a linear homogeneous equation, call it equation 1, 2x1 minus 3x2 plus x3 equals 0. And we have some other homogeneous linear equation like minus x1 plus x2 plus 4x3 equals 0. Okay, then we could take one subspace to be all the points that satisfy equation 1, and we could take U2 to be all the points, this is all the points in F3. That satisfy equation 2, right? Okay, and so then what we have is that each one of these guys is going to be a plane in F3, plane through the origin. And in fact, if you look at this equation right here, you'll see that that can be rewritten as 2 minus 3, 1 dot product with x equals 0, and that is in fact the formula for a plane, right? So the plane looks like a fixed vector, which is going to be your normal direction, times x being equal to, and then in general a constant. For us, since it's homogeneous, the constant will be 0. All right, so let's come back and take a look at U3, and we'll define that to be the intersection of U1 and U2. So this guy, turns out that unions typically aren't subspaces, but intersections always are. And that is one of the homework exercises. Exercise number 10. So then, since intersection corresponds to an AND condition, that means that U3 is going to be the collection of points that satisfies equation 1 and equation 2 simultaneously, right? And so if we write the matrix A as 2 minus 3, 1, negative 1, 1, 4, then U3 is going to be the collection of points such that AX is going to be equal to 0. And you can see that from the way that matrix multiplication is defined in terms of dot products. So we don't need to make this precise. We haven't talked about matrix multiplication formally yet in the course, or dot products for that matter. I just wanted to sort of point this out as a way to tie these things together. And so note that this 0 here on the right hand side, this is actually 0, 0. And so there's actually two equations being satisfied in that single matrix equation there. And you can also see a couple of other things. So if we had an equation which was not homogeneous, right? So like ax equals b, or if we had a nonlinear equation, then if you take x and you replace x with lambda x for some lambda other than 1, this will break the closure axioms. So this is just a way to see that if your equation is not homogeneous or if it's not linear, then you end up not getting a subspace. And the reason why is just because this substitution will break one of the closure axioms. So what that gives us then in the end for this example that we were looking at is we've got U3, which is a subspace of both U1 and U2, which are both subspaces of F3. And so the implied containment symbols are going like this. This is called a lattice of subspaces. Sometimes they get complicated. We won't have to mess with them too much.